Alright, so in this video, let's discuss how we're going to apply a twist to our spine so that when we rotate our shoulder controls in Y relative to our hip controls, our spine will end up with a twist going along the length of the bones. Now if we quickly grab a rotate tool and were to grab one of the bones in our spine, you can see that for the twist we want to be rotating our bones in Z. However, we can't just rotate the bones in Z because we know they're being driven by IK, and that means that the IK is going to override those bones' rotation parameters. And we can't just jump down into the chop network and modify the IK data. If we jump over to the whiteboard, we can discuss that for a second. So you might think to yourself, well, okay, we know we want to have a rotation in Z after those IK-driven rotations, so why not just add some kind of value into the Z rotation and then reference that newly changed rotation onto our bones? The problem with that, of course, we could have something that looked like so, driven by our IK, and if we were to rotate this lower bone around Z, that's going to occur after the IK. So the IK's come in and it's determined that this second bone in the chain needs to have a certain rotation to give it a specific orientation. And then after that point, we've come in and we've rotated in Z. And that's going to then rotate this bone after its rotation in Z into the incorrect position. And this will only get worse if we then rotate this bone in Z, and so the next bone that would have been in the chain would then get rotated as well. And so we're going to end up, if we did that, with a spine that doesn't follow our curve at all. So we need to come up with a different approach. What we can do is wire nulls in between all of our bones. So if we imagine that we've got our spine, we've got 5 bones in our spine, so let's say that 1, 2, 3, 4, and 5. So let's say we had a spine that looks something like that. It's probably shaped slightly differently, but this would be fine for our demonstration purposes. We can wire nulls in between all of our bones. So currently in the network, if we just draw this out as if it was going from bone 1 down towards the top of our spine, so we're having the network in a normal order as opposed to how we reordered it in the network editor, because this is going to be a little bit clearer to demonstrate. So we've got our bones, and each of the bones is parented directly to the bone just beneath it in the spine, which means that obviously they're going to come in with their position at the end of the bone, not at the start of the bone. But if we were to come in, and I'm just going to draw this out in one case as opposed to for multiple cases, if we were to come in and instead of having a bone directly parented to a bone, let me grab the eraser. Fantastic. And then grab the brush. So let's say that in between those, what we do is we wire in a null. So we're going to say that this is a bone, this is a bone, but this is a null. And with this null, what we need to do, obviously now we have a bone parented to a null, which means that bone is going to come in with its origin at the null's position, but we have a null parented to a bone, and that means the null is going to drop back down to the start of the bone, the origin of the bone, because it's only when we parent a bone to another bone that they come in at the end of the bone, as we discussed back in Technical Rigging 1. So we need to make sure that this null gets offset down the length of the bone to the end. But once we have that in place, if we simply have nulls that sit in between, that won't break our inverse kinematics. That's going to allow us still to have our inverse kinematics driven by that curve that sits underneath the bones, and inverse kinematics will still come in, it will still work out the rotations needed to apply to those bones, and everything will still function. So all we've done now, we now have a null sat on the end of every bone from the first bone all the way up to, but not including the last bone. So in between each of the bones, we're going to have a null that sits in between. It's going to act as a buffer. And the null isn't being driven by inverse kinematics. The null is just there as an object, which means we can now jump in and we can start working with their rotation parameters. If we were to rotate the null, which we know now is oriented for our bone, if we were to rotate that null in Z, which you know again is going to rotate around the bone, we rotate each of those nulls in Z, and that will have the end result of rotating the bone that attaches to that null in Z, which to begin with is going to make you think, hey, that's going to do exactly what we said we didn't want to do and cause our bone to rotate off of the curve. However, inverse kinematics will jump in. It will notice that our bone isn't hitting the curve because of the fact that we're not changing that inverse kinematics data. We're working with the objects themselves. So it's going to actually notice that the inverse kinematics bone isn't on the curve, and it will calculate new rotations. But those new rotations that are calculated are going to keep that rotate Z that we just created, which means that if we rotate these nulls, we're going to be able to rotate the bones but still have them follow that curve. What we can do for each of the nulls, we know in this case we've got 5 bones, we're going to have 4 nulls. If we apply 1/4 of that total twist rotation to them, as we move up the spine, we're going to get 1/4 applied here, then another 1/4 applied here, which means we now have a total of 1/2. We're then going to get another 1/4 applied here, which means we have a total of 3/4. Finally, we get that final 1/4 applied here, which means as we move up the spine, we'll get more and more and more twist until the top of our spine has that full twist amount, whilst the bottom of our spine is completely unaffected. So we can wire nulls in between each of our bones, apply a fraction of that twist rotation to them, and that will allow us to, by the end of the spine, have the total twist rotation. So let's talk for a second about how we're going to calculate the twist angle that we want to use. So I'm going to bring up a new layer. Fantastic. Let's scroll up. Fantastic. So what we want to do, we want to calculate the twist angle, and really we said that needs to be the relative difference between our shoulders and our hips in terms of their rotations in Y. We know that if we rotate our shoulders around in Y, then we want our twist to obviously follow along with that. But if we were to rotate our hips back in Y, we'd actually want our twist to take that into account and become greater at the top, so that we know that the back has now rotated round. We need to cancel that and then still do that original twist that we had. Of course, if our shoulders are attached to the hips, then we know that rotating the hips will also be rotating the shoulders, and that's fine. We just need to calculate the relative difference in rotate Y. And you may think to yourself, hey, relative difference, we can use the origin expression. Unfortunately, relative difference when working with rotations becomes a little bit trickier, and we're actually going to bump into this problem a little bit later when we look at matching our attached and detached controls. So you see, we're dealing with relative rotations, but we need to be dealing with the complete rotation. Let's think about this for a second. If I was to say, what is the difference between our shoulder control and our hip control based on an origin expression, it's going to say, well, let's say that our shoulder control in rotate Y happens to be facing this way, and our hips happen to be facing this way. It will say, oh, that looks like 180 degrees. Or it may come in and say, oh, that looks like a negative 180 degrees. Either way, it will find the difference in the angles. But what if we hadn't only rotated 180 degrees? Or what if we hadn't only rotated a negative 180 degrees in order to get to our new shoulder position? What if we'd gone all the way through 360 degrees and then back around another 180 degrees? The origin expression is just going to see this as the difference between the two and give us 180 degrees, when we know we really need 360 plus 180 degrees. Worse than this, if we were to rotate slightly further, it's now going to find the shortest distance between those and give us something that's just below a negative 180. Let's stipulate a negative 170 degrees, even though that now we should have been 360 plus 180 plus a further 10 degrees. So you can see, using the origin expression, because of the fact that to the origin expression 360 degrees is the same as 720 degrees, it's the same as 0 degrees. It doesn't account for going through a complete revolution and continuing. And rotation parameters themselves, however, do account for going through a complete rotation and continuing. If I rotate my control to 360 degrees, we'll have a parameter, our rotate Y parameter, that says 360 degrees. If we continue rotating a further 180, we're going to get a rotate Y that equals 360 degrees plus 180 degrees. So we're going to get that complete rotation. We're not going to get that suddenly cycle back round and cancel that 360 when we get to 0 degrees. So how are we going to deal with this? Because we have 3 different rotational parameters we need to take into account. we have our attached shoulder rotations, our detached shoulder rotations, and in some cases we need to also take into account the rotation on our hip control. Let's talk about the most simple case, and that's with our attached rotations. With our attached shoulder control, we know that it is parented into our hip control. That means any rotations on our hip control get applied to the shoulders, but not in terms of their rotation parameter. We just get that in terms of parenting. That means that we don't need to worry about what our hips are doing, because whatever our hips do, our shoulders are going to inherit. That means that when we're dealing with our attached control, we simply need to look at what is the rotation in Y on that control. Because whatever we've put the rotation in Y on that control, that is the relative difference from our parent. That is the relative difference from that hip control, which is the exact rotation that we need to apply as our twist angle. So when we're dealing with the attached control, we can simply take the attached control's rotation in Y. However, when we're dealing with the detached control, we know that if we rotate the detached control, we're going to get a change that we need to apply in twist. But if we're to rotate the hips control some way in the same direction as that twist angle actually needs to get smaller. We can imagine this, that we have our base and then we've got the top. If we rotate the top, then that means as we go along we need some kind of twist. But if we were to rotate the bottom, that's going to start to undo that twist. So we need to basically find the difference between our detached shoulder controls and our attached, or rather hip controls, and we can take the detached shoulder control, subtract the hip control rotation from that, and that will give us the result. Now this works because they're both parented into the master control, and that means they're not getting any other form of rotations in Y apart from what is being applied to them in their rotational parameters. So that means we can just do a difference and know that is the relative difference between the two. And this is going to work in both cases. If we were to rotate our hips control to give them a slight positive rotation, while our shoulder control already had a positive rotation, the difference between the two is now going to give us a slightly less of a twist angle, which is exactly what we want. We've rotated our shoulders, but now we're rotating our hips to match. There's less of a difference between them. We want less of a twist angle. On the opposite way, if we were to rotate our hips in the opposite direction, that's going to get a smaller and smaller and smaller angle on the hips, which means that we're going to take less and less and less away from our shoulder control and get more and more and more of a twist angle. So that is indeed going to work. Now, in order to make the change in rotation Y with our rotate tool, so when we come in with the rotate tool or the show handles tool and we use the handle to rotate in Y, I want to make sure that we have that tool have a more direct correspondence to our twist angle. That means that when we rotate in Y, I want it to only modify the rotation in Y parameter and not affect the rotation in X and rotation in Z. In order to do that, I'm actually going to change the hip and shoulder control rotation order to have rotate Y, rotate X, rotate Z. That means that rotate Y is the most important rotation now, not rotate X. That's the rotation that is applied last, which means if we change rotate Y using the rotate tool, that means that we're going to have that rotation only affect our rotation in Y parameter. Granted, when we rotate in X and we rotate in Z, it's possible that that will cause changes to our rotation in Y. But the main thing is if we were to come in and rotate in Y, we do want that to drive that rotation in Y parameter, since that's going to be driving our twist angle. So you can see that with this setup, we now have the ability to compare between the two control objects. Once we have that twist angle in place, we can then send that back over to our nulls, making sure that we apply a fraction of that angle to each of our nulls, and that will give us the twist up our spine. So that's going to be the focus of the next video, and then from there we can take a look at those 3 spine controls and how we can get those to work based on that twist angle as well. So that is going to wrap up this video. Thanks a lot, everyone.